So today we want to prove this concept here, and it's also from AOPS, Introduction to Number Theory. So it says if n is a natural number and n is greater than 1 and it has no prime divisors less than or equal to root n, then n is prime. Okay, so how do we prove this? Well, we know that a prime number basically means n has no divisors other than 1 and n. So let's start with proving the opposite of this. So I want to prove that if n is a natural number, n is larger than 1, and it has prime divisors less than or equal to root n, then n is a composite number. Okay, so now I just want n to be a composite number. And basically, I want to say that, so by definition of composite numbers, I know that n is equal to ab, for both a and b being larger than 1, and a and b being less than n. Okay, so now I want to prove that, let's say b is larger than a. Now I want to prove that b is gonna be larger than or equal to root n, and a is going to be less than or equal to root n, and obviously these conditions also are satisfied. Okay, so how do we prove this then? Let's start proving the contradictory of this. So I want to say that, okay, so I can have both a and b, to be larger or equal to root n. Okay, so if in that case, if I multiply a times b, that should give me n, right? ab is equal to n. However, if I have my inequalities written separately, then I have b is larger than root n and a is larger or equal to root n. So ab, in this case, is larger or equal to n. So only in the case when I know that ab is not larger or equal to n. ab is larger than n because I know that b is larger than root n and a is larger or equal to root n. So basically the smallest value of these two are just larger than n. Of these two is larger than n. So basically, because root n times root n is n, and b can't be root n, it has to be larger, then a times b is going to be larger than n. Okay, so this contradicts with our theory of having n equals a times b. So this part is obviously not true. So this part, let me just box this, is not true. So since that's not true, we know that b has to be, so we know that one of a and b, in this case a, because a is less than b, has to be less than or equal to root n, while the other is larger or equal to root n. Okay, so now we've proven this part here above, then we know that when n is a composite, we have b is larger or equal to root n and a is less than or equal to root n. So that means that, any natural number, so we know that any natural number n which is not a composite and is greater than 1 is gonna be a prime number. So we know that for any prime number, these conditions aren't gonna be satisfied for prime numbers. So we know, and for prime numbers, we have n is equal to 1 times n. That's our only way of prime factorizing, or that's not even prime factorizing, but that's our only way of writing n as a multiple of two other natural numbers. So we know that here, if n is a natural number, n larger than 1, and it has no prime divisors less than or equal to root n, then n is prime, because 1 is actually not prime. So 1 is not a prime divisor. And if we had any prime divisor, a, that is less than or equal to root n, then we had a b that is larger or equal to root n. So this just tells me that if this condition is satisfied over here, then I have my n being a composite number. N isn't prime. So if this condition isn't satisfied, then n is prime. So that's just the logical sense here. So if n isn't composite, then it's prime, because n is greater than 1. 1 is a special case because we know that 1 is neither prime, neither composite. So thanks for watching.